We'll go ahead and get started this morning. Thanks for joining us, everyone. Again, my name is Jason Vandiver, Energy Code Program Manager for SPEAR. I don't put the SPEAR introductory slides up there anymore. I assume most of you folks know who we are. We're an energy efficiency organization serving Texas and Oklahoma. What I've been doing a lot of lately for you code officials on the webinar today, recently did one down in McAllen, Texas, where we did a 2-hour classroom presentation, covered a little bit of HVAC, residential 101, manual JS&D. We can do a little energy code overview, insulation installation. But what's more valuable is we had 41 people, 7 different jurisdictions represented with inspectors out in the field. We spent almost 3 hours in the field walking residential homes under construction. If you would be interested in that classroom and or field training in your jurisdiction, just shoot me an email. I'd be happy to help you out. You will get a little bit of housekeeping. We are an ICC preferred provider. To get your ICC CEUs, you will get a course evaluation. Just fill out the course evaluation, and in that course evaluation will be the contact information for SPEAR. So if you're interested in some of the field or classroom training, just get a hold of us, and I'll be happy to set it up. The classroom and the field training does come with ICC CEUs. So, it's a good way to get 4 or 5 hours of CEUs, and I'm telling you, the field training is invaluable. Slides are great and all, but actually walking a job and putting our eyes on things together, it's a super valuable training. And I can't help but pull the bullet, have my building official hat on, and we'll look at electrical and plumbing and the framing, the weather resistant barrier. We look at it from top to bottom and go completely through it. Drainage, everything. But that's not what we're talking about this morning. We have an overview of the VRF industry, and I'm happy that Corey Hines is giving the presentation for you. Corey certainly knows what he's talking about. He's a registered professional engineer, and he's currently the business development manager for Daikin. In that role, he develops basically relationships with engineers, architects, building owners, which increases the Daikin products in the North Texas area. He has over 17 years experience in the HVAC industry, multiple roles. And during the past 9 years, Corey's focused on variable refrigerant flow sales and applications. Daikin is as prominent a manufacturer for that industry as there is on the planet. I've toured their facility. It is super impressive. It's just unbelievable. Mr. Hines earned his his MBA at SMU University in 2008. He also has a Bachelor of Science in Architectural Engineering from the University of Florida. He's involved in professional and civic organizations, including the Real Estate Council of Dallas and Fort Worth Club. His hobbies include gardening, golfing, fishing, skiing, dining, and travel. I've got a couple of those in my hobbies as well, switch skiing for snowboarding. And he and his family reside in Princeton, Texas. So with that, Corey, take it away.
Hey, Jason, thanks so much. And thank you for the opportunity to be here today. Thank you, everyone, for coming today. And today we'll be talking about the VRF industry. We'll be talking about we'll be giving you an overview and trends that are happening. Got lots of code changes, things that we'll be discussing this morning. So appreciate your time. So first, I'll give you an industry overview for VRF. Next, we'll talk about code implications and industry trends, and then we'll end with questions and answers. So VRF is a very modular product. The main components are outdoor unit, indoor unit, piping, controls, and ventilation. Very simple system when you think about these 5 components. Traditionally, VRF has been utilized over the last several years, has grown very rapidly. We started out being known as the chiller killer, and that's why I show an image of a chiller down below. You'll see that a chiller has a lot of complex components. We have ducts, valves, controls, balancing, and VRF is just a lot more simple and provides comfort cooling, energy efficiency, and easy maintenance. So let's talk a little bit about the different components within a VRF system. Like I said, we're a very modular product. We consist of an outdoor unit. That outdoor unit has a inverter compressor inside of it. An inverter compressor, think of a VFD. Imagine having, you have a VFD on a fan. That VFD allows that fan to speed up, speed down. The inverter compressor does the same thing inside the outdoor unit in a VRF outdoor unit. So we're able to speed up and slow down that compressor. We can modulate from 10 up to 100%. And at 100%, we're actually spinning faster than 60 hertz. And so that allows us to have a lot of head pressure and low temperature applications. And then our indoor units, we're variable at the indoor unit as well. We have an electronic expansion valve, and that expansion device is going to open and close. It's going to modulate hundreds of steps of incremental capacity potential inside of it. So we can actually provide the right amount of refrigerant flow across that coil at any given time. We also, another product that is very prominent in our industry today are mini splits. And a mini split consists of an outdoor unit and an indoor unit. And inside the mini split, we have in the outdoor unit, we actually have an inverter compressor, once again, that is able to speed up, speed down, or slow down. And we also have an electronic expansion valve. Instead of it being at the indoor unit, it's actually inside the outdoor unit. So that's one of the main key differences between a VRF system and a mini split. So the VRF concept, as we look at larger commercial systems, we actually, we're known for having a single outdoor unit or a gang of outdoor units that have been linked together. We can have up to 3 air-cooled modules tied together to form a single system. And that single system has multiple indoor units downstream. And as I mentioned earlier, those indoor units each have their own expansion device that opens incrementally. And that allows us to provide the right amount of heating or cooling capacity needed at any time in a single space. So we can actually have up to 64 indoor units on a single outdoor unit system. And these systems, not only do we have an air-cooled option, but we also have a water-cooled option. And one of the unique things about the water-cooled option is that we're going to actually have a ground source or another water source, such as a lake or cooling tower, tied to that outdoor unit through a heat exchanger. And that outdoor unit is going to reject heat to that water source, whatever that is, when we're talking about the water-cooled VRF system. And we'll also add a boiler to that system so that we can keep our temperature constant year-round and provide the best efficiency possible with that system. So once again, that's also a water-cooled VRF system. The only difference is we're rejecting heat to water as opposed to rejecting heat to the air like we would with an air-cooled system. And once again, we have multiple indoor units tied to a single outdoor unit, and we're able to provide comfort cooling in individual spaces. So we have 2 different types of VRF systems. We have a heat pump. Think of a 2-pipe chilled water system. With our heat pump VRF system, we're going to have all of the indoor units will be in the same mode at the same time. They'll either be in cooling or in heating. And of course, in this example, I have a 6-ton heat pump with 2 indoor units downstream, and they're in heating. And then just below that 6-ton outdoor unit, I have an 8-ton outdoor unit with 2 indoor units downstream in cooling. So all those indoor units on that 6-ton system are going to be heating when we call for heating. And on that 8-ton system, we're calling for cooling. So all those indoor units downstream are going to be cooling. By comparison, by contrast, on the right-hand side, bottom of the screen, I have a 14-ton outdoor unit. And that outdoor unit is a heat recovery system. So different model number than the heat pump outdoor units. So this heat recovery outdoor unit has a special device we call a BS box downstream, and that BS box allows us to have simultaneous heating and cooling. And the way that happens is that we're able to provide through the BS box hot gas for heating or subcooled liquid for cooling. And actually, on a day when we have heating and cooling occurring at different times during the day and in different parts of the building, we can actually take all of the energy that goes into heating and put that into cooling energy for the system. And this is called a heat recovery system. So it operates a lot like a 4-pipe chilled water system where we can have simultaneous heating and cooling. In a 4-pipe chilled water system, that heating comes from a boiler. And we have 2 different coils inside of the indoor unit. But with VRF, we have a BS box. It's going to allow us to have that indoor unit switch over from heating to cooling and provide hot gas or subcooled liquid as needed. So where did VRF begin? One of the reasons VRF came about was because of the rapid changes with regard to energy during the late 70s. And VRF was actually born in Japan as a result of the oil embargo and that rise in energy prices that occurred during the 1970s. And you can see here the sharp spike that occurred due to the Arab oil embargo and the subsequent rise in the energy prices per barrel. So the idea was to use individual indoor units, allow individual indoor units to deliver heating and cooling to only the occupied spaces in the building. And so began the birth of VRF. And future evolutions allowed us to provide more energy efficient features to further improve the operational performance of the system. So the world's first VRF system was actually developed in 1982, and that system was developed by Daikin. And other changes and in technology that occurred in VRF technology down the road included the introduction of the first inverter compressor in 1990. The heat recovery VRF system, the first one was introduced in 1991. So that's a system that allows the simultaneous heating and cooling. And in 1998, we actually created single phase VRF technology. One thing I want to point out is that all of these innovations, including the invention of the first VRF system, actually occurred through Daikin. And further innovations that have happened, a lot of the firsts within this segment of the HVAC industry have occurred through Daikin. So in 2002, there was the introduction of water-cooled VRF technology, and 2003, the first R410A VRF system was introduced. And then in 2014, hybrid systems with R32 were introduced, as well as refrigerant temperature algorithms, which add up to 60% more energy efficiency. So you'll see in 2003, a lot of VRF manufacturers actually began to enter the North American market. So around 2003 is when we saw the first 2 major players in VRF enter the North American market, whereas VRF previously had been all over the world by the time the early 2000s came. So VRF history in North America. So the first entries, first companies to come to North America with VRF were Mitsubishi and Daikin, followed by LG, Sanyo, Samsung, and now they're actually up to 11 major manufacturers of VRF, as you can see by the graph here. And there are actually 24 different 3-phase VRF brands that are currently listed in the AHRI directory. Key drivers have been energy prices, legislation, environmental awareness, utility rebates, competition, and market awareness. These actually have helped propel the amount of VRF systems in the market as as they relate to the total amount of total share of equipment sold in the marketplace. So you can see the adoption of mini splits and VRF technology has been very rapid. Starting in 2010, you can see that there were about 300,000 mini splits being sold annually. As of 2016, that number is more than doubled to over 700,000 units per year. This has happened because of more efficient cooling of targeted zones, reduced energy losses in ductwork, application flexibility, which would include things such as the ability to add on noise, etc., and then contractor appeal. And then presently today, VRF represents approximately 10% of the commercial HVAC market as of 2017, and up to 15% of the residential HVAC market. So annually, we've had over 20% growth between 2017 and 2018. And so we expect this expansion to continue. So how are the VRF and mini split systems rated? They're rated according to AHRI 210 and 240. And AHRI 210, 240 align the federal test procedures for residential AC equipment and heat pump systems for capacities less than 65,000 BTUs. And this legislation, this standard, defines the SEER ratings, the EER ratings, and the heating ratings, HSPF ratings for mini splits. And then for systems larger than 5 tons, AHRI 1230 defines the performance for requirements for VRF systems. And in 2011, AHRI 1230 was released to provide testing and performance guidelines for the VRF industry. And the latest version of AHRI 1230 is the 2014 version, which includes Addendum 1. And this covers the air-cooled and water-cooled VRF systems. 1230 defines up to 5 performance metrics for each system. So those metrics include EER at 95 degrees Fahrenheit, IER, which is the system's seasonal cooling efficiency, the COP, which is at 47 degrees, which is the full load heating performance at 47 degrees. And then there's a second heating performance, which is called the coefficient of performance at 17 degrees Fahrenheit. And that's the full load heating performance at 17 degrees. And then several years ago, another key metric was defined as, which is called SCHE, which is simultaneous cooling and heating efficiency. So that describes the efficiency of the VRF system on a day when we might have simultaneous heating and cooling occurring in a building. By the way, SCHE is only applicable for heat pump systems with heat recovery. AHRI 1230 and VRF performance ratings. To account for variances in system performance associated with a wide range of application possibilities, AHRI 1230 defines the tested combination system types. So there are actually 2 different types of systems. There's a ducted tested combination and a non-ducted tested combination. So when you review the AHRI 1230 ratings for a given manufacturer, you'll see the terms ducted and non-ducted. And you'll see that the ducted indoor units actually have slightly less efficient than the non-ducted systems. So these systems account for increased piping length for the larger systems as well. Typical AHRI performance ratings, this is kind of what they look like. So like I mentioned earlier, typically the non-ducted indoor units are slightly more efficient. So that's going to be our 4-way cassettes and high wall indoor type units. So you'll see that typical ratings for non-ducted systems starting at 6 tons or higher. So then at 8 tons, they kind of peak. We're right around 30 IEER. So IEER, that's the integrated efficiency ratio. So that actually truly defines the performance, looking at specific performance points for each size system, all the way from 6 tons up to 38 tons. So IECC 2015 for commercial buildings. So there are different performance compliance paths for VRF systems, and these are determined by the local state government or the local city. And so some of the different requirement paths, the first path is IECC. So IECC, currently in Texas, many cities are utilizing 2015 and switching over to 2018. And you can see that there's some mandatory requirements. If you're looking at IECC, for example, section C403.2. And so the way that VRF systems are compared and managed through IECC entail the reviewing section C403 for mechanical, then going to C406.2, which calls for more efficient HVAC performance. So by definition, we're looking for VRF systems to be at least 10% more efficient. And then we also look at the secondary path, which you can see at the bottom of the screen, is ASHRAE 90.1-2013. So engineers will utilize one of these paths to define how the VRF system will be applied to a building. And one of the reasons for using the prescriptive path is to help define or determine whether or not economizers will be needed. And typically a lot of engineers will use the ASHRAE 90.1 path. That prescriptive path allows us to make the installation of the system easier by eliminating the economizer requirement. You can see that in Texas, we actually fall in zones that do call for economizers, particularly the brown area that you see around the state of Texas on the screen. So this prescriptive method is used quite frequently. So when it comes to the economizer requirement, the key exceptions are for climate zones 1A, 1B, looking at the previous slides, systems less than 54,000 BTUs, systems that operate less than 20 hours per week. And then there's also, number 4, an efficiency trade-off, which is what the table 403, table C403.3.1 talks about. So in climate zone 2B, we're looking for efficiency performance that's greater than 10%. In 3B, we're looking for efficiency performance that's greater, equal to or greater than 15%. And then in 4B, we need to have efficiency that's greater than 20%.
While you're on that slide, Corey, I'm sorry to interrupt, but just for the code officials on there, this is a major headache. Climate zone 2B, well, a dry climate zone 2 is what B is. So we don't have to have an economizer. We can have more efficient equipment there, but where you typically are more, it's more appealing to bring in dry outdoor air, whereas Houston, climate zone 2A, you can't do more efficient equipment in lieu of an economizer, which is broken in the 2015 Energy Code. They have fixed this in the 2018 Energy Code. It no longer specifies B. So for those code officials, so when I was a building official, I could always accept a newer code as compliant. And so I would encourage you code officials that are still on the 2015 energy code to ignore this B, because they fixed it in the 2018. And so if you want to allow more efficient equipment in lieu of economizers, which I can guarantee you the mechanical contractor would choose to do 9 times out of 10, I think you are well within your right, and you're meeting a newer, more stringent code in the 2018 with that. And frankly, this was just broken in the 15. So that's all I had to say real quick on that.
Sure. Hey, thanks, Jason. Appreciate that. So how do we address economizer challenges? It's going to depend on the climate zone. The designer may be able to trade off the high cooling efficiency against the requirement for an economizer. We'll use modeling. That's generally what has to happen if an engineer takes the prescriptive method using ASHRAE 90.1. And then we do apply economizers to ducted fan coils when necessary. So the evolving nature of economizers and decentralized HVAC, as Jason pointed out, IECC 2018 expands the possible climate zone exemptions. So it does include 2A and 2B. Still have to meet the efficiency improvement requirements per zone. So for 2A, 2B, it's 10%, 3A, 3B, 15%, 4A, 4B, 20%. And ASHRAE 90.1 2016 actually expands the exemptions for economizers. So we actually have 11 economizer exemptions, including 15 climate zones for increased equipment efficiency. And this still does require that all fan coils greater than 54,000 BTUs have economizers unless the system meets the increased efficiency target for the climate zone. ASHRAE standard 15. So ASHRAE 15, this is something I know we covered it at length several months back last year. The purpose of ASHRAE 15 is to specify safe design, construction, and installation of VRF systems, particularly of VRF systems, but specifically operation of refrigerant systems. This establishes safety for occupants in buildings, and applies to the design, construction, modifications, and then substitutions for systems that have a different designation. So there are different occupancy classifications. Those main classifications include institutional, public assembly, residential, commercial, large mercantile, industrial and refrigerated rooms, and then mixed. And mixed is when we have 2 or more occupancy types within the same building. So what we'll do is we'll apply the rules to the occupancy that has the most stringent requirements. So there are 5 key different types of systems defined in ASHRAE 15. We have a direct system. We have an indirect open spray system, a double indirect open spray system, an indirect closed system, an indirect vented closed system. And VRF systems are classified as high probability systems, as are other equipment types such as PTACs, water source heat pumps, packaged rooftops, and DX split systems. Within ASHRAE 15, there's or actually ASHRAE 34 defines the classification of refrigerants. So we actually have 3 different classes. Class 3 is high flammability. Class 2 is lower flammability. And Class 1 is no flame propagation at all. And then there are actually 8 different safety groups. Those safety groups are defined as A, which are lower toxicity safety groups, and then B, which are higher toxicity safety groups. And then we elevate these different safety groups. We go from A1 and B1 up to A3 and B3, depending on their flammability. So A groups are lower in toxicity, B groups are higher toxicity. R410A actually is classified as an A1, refrigerant. Thus, it has low toxicity and no flame propagation. And as you continue to look at the tables in ASHRAE 34 and then also look at ASHRAE 15, you'll see that there is a refrigerant concentration limit. And that refrigerant concentration limit, or RCL, that's the allowable concentration of refrigerant in air as determined by ASHRAE 34. And this helps us, make sure that we don't put too many toxic substances inside of an environment. So the concentration of refrigerant is defined by ASHRAE standard 15, whereas 34 defines the toxicity requirements. So you can see that within ASHRAE 15, there's a table. It looks like the table I'm showing here on the screen. And here on this table, I'm showing just some key refrigerant types. So we've got R22, R410A, and you can see called out here within this table, we have ASHRAE standard 34 classifications. We have an occupational exposure limit, or an OEL, which is in parts per million. And then we also have a refrigerant concentration limit, which defines the maximum pounds per 1,000 cubic feet that we can have within a space at sea level. So R410A, for example, has a ASHRAE standard 34 classification, which I mentioned in the previous slide, of A1, occupational exposure limit of 1,000, and a refrigeration concentration limit of 26 pounds per 1,000 cubic feet at sea level. So when we apply ASHRAE 15 to VRF systems, we go through 4 different steps. We want to determine the volume of the smallest occupied space. Next, we want to determine the refrigerant quantity potential of the smallest occupied space. Next, after that, we want to check that the refrigerant quantity potential does not exceed the allowable RCL, or refrigerant concentration limit, per 1,000 cubic feet. And then we want to check the routing of piping. It has to be non-obstructive within corridors, lobbies, versus the RCL requirements. So that's step 4. So what do we do if a room is too small? Well, we have 2 different options. We can reduce the concentration level, or we can increase the dilution volume. So reducing the concentration level revolves around reducing the total refrigerant charge within a system. As I mentioned earlier, the VRF systems have the ability to be individual outdoor unit modules. We typically use air-cooled systems, by the way, so I'm going to use an air-cooled system as an example here. We can actually have a dual module, which is 2 modules tied together to be one system, or we can have individual modules. And then another option is for us to have a 3-module system. So really doesn't matter, whether or not we have a 2-module, 3-module, or a single module system. The cost to install that system is generally still the same. So a good design, a good way to design a system is actually to have single modules, and maybe here and there have some dual modules. So this helps us reduce that refrigerant concentration limit, partly because it's going to help us reduce the overall system piping lengths. So by optimizing the module sizes and the piping length sizes, we can actually reduce the amount of refrigerant that we're going to send to a space. So there are 2 different types of spaces. We have connecting spaces. That's where we have spaces that are very isolated. They don't have any permanent openings. We also have ventilated spaces where we're going to have the ability to ventilate that space. And within ventilated spaces, we actually have 3 different ways that we ventilate spaces. It can be through a closure, which could be a damper or an undercut and a door. We also have plenums, although we can't really include the plenum in that space volume within that ventilated space. And then we have supply ducts and returns. And the volume of those ducts and returns have to be included when we calculate the refrigerant quantity within that ventilated space. So how do we increase the dilution volume? One way is to have door undercuts or a transfer grill. And you can also see here a third way would be to have a partition wall. So 3 different ways. These create permanent openings between spaces and allow us to actually increase the actual volume of the space, which reduces the overall refrigeration concentration limit because we have transfer of air between those spaces. We can also dilute the volume of a space by having a single ducted indoor unit serve 2 spaces that are tied together. And that allows us to serve multiple spaces, actually can help us cut costs in a building, and allows us to further increase that dilution volume. We can also use the void space as a plenum changer, which is method 2. We can also increase the floor-to-floor height within a space, within a room. So a lot of rooms, a lot of buildings have false ceilings. So by increasing that false ceiling, which our VRF units allow us to do that because they're smaller, take up less space in the ceiling. That's another way to further increase the dilution volume. So what is the future of refrigerants? Over the next few years, or next several years, all of the VRF manufacturers, all the HVAC manufacturers rather in North America are going to be asked to start looking at other refrigerants. And so currently everyone uses R410A, but that will change. Regulations in California are looking to drive the HVAC industry forward. So California state law requires reduction in greenhouse gas emissions to 40% below 1990 levels by 2030. One of the ways to reduce those greenhouse gas levels is to change refrigerants. And part of that is to reduce the use of HFCs such as R410A. An industry agreement has been signed, and so it asks us by 2023 to lower our global warming potential of refrigerants. And this is going to be based on the date of manufacture. So that means that, even after January 1st of 2023, when this legislation goes into effect, we may still end up seeing R410A products out there that were manufactured before that date. However, we'll have the opportunity to continue to sell those products for another 6 months. This ban will exclude chillers. So what is the future of refrigerants for VRF? So what we see happening in the future of refrigerants for VRF is that R410A will go away, won't be an option by 2023, which is less than 3 years from now. Many manufacturers are going to move to R32, which is a refrigerant actually created by Daikin, and the patent was opened to allow other manufacturers to use it. And R32 has already been globally adopted in many VRF systems in Europe and Japan, including some PTACs that are already being manufactured and used in the United States. The advantage of R32 is that the ozone depletion level is 0, and the global warming potential is lower than that of R410A by a factor of more than 3. So R32 is classified as an A2L, which says it's lightly flammable. So when you look at it on the chart, it is a class 2 refrigerant. Other manufacturers are also considering a class 2 refrigerant with an ATL of or a safety that fits in the safety group of A2L, and that refrigerant is called R54A, R54B, and that refrigerant has already been adopted by Carrier for ducted residential and light commercial package equipment for 2023. So we will see the VRF industry continue to outpace the other equipment traditionally used for residential and commercial HVAC industries. The reason people want to use VRF is because of the zoning, the energy efficiency. There's also a faster installation for contractors as well, which means higher profit margins. There will be some code changes and adjustments that will need to be considered over time for VRF system implementation. We'll continue to look at economizer requirements. Sometimes economizers are not simply physically feasible for non-ducted indoor units. And there will be further studies to validate the cost benefit of economizers when it comes to VRF. And the refrigerant changes and focus on global warming will also be another important factor as we look at the future of our HVAC industry. That's all I have today. Really appreciate your time, and happy to answer any questions that you all may have today.
Alrighty. Let's see. As far as the testing procedure, the AHRI 210, 240, I've heard that that full load is somewhat unfair to the VRF equipment. Can you expand on that a little bit as far as how the testing is and how the efficiency, or has that been fixed?
Right. Yep. So that has been fixed. We actually define the efficiency of products with 2 stages or inverter compressors. Their true efficiency is defined by a criteria called the integrated efficiency ratio, which is IEER. And that IEER actually describes how efficient the system is at different temperatures at different times throughout the year. So it's a formula that looks at 4 different points and in time, as the equipment operates. And so it actually better defines the efficiency than EER. EER looks at the full load capability, and actually depending on where you're located on this call today, we're in the 50s and 60s across the state today. So HVAC systems such as VRF or mini splits, they're providing cooling or heating today, but they're not doing, they're not operating at their peak, which is what EER does. Instead, they're operating at one of those lower points, which is what IER defines. So it actually defines a true efficiency, which is actually greater than the EER.
Okay, and then a kind of a similar question. So when I'm reviewing plans and I'm allowing the economizer exemption, what number do I need to be looking at to find that 10 or 15% to know that it's more efficient? The equipment's more efficient.
We'd be looking at the IEER.
IER, okay.
Yep.
And then you just compare that to the code values if it's
right.
Okay, and then 10%. Okay,
yep.
And then everybody's quiet this morning. I had only 2 questions. You must have been very thorough in all of your explanations, Corey. For everybody on the webinar, you will get a PDF of the slides. Corey's contact information is on the last slide there. So if you think of a question later and want to reach out to him, there's his contact information, and that will be part of the PDF that everyone gets as part of this. Also, I will include, I basically took because this is part of our SECO HVAC webinar funding, I have taken the residential chapter the mechanical chapter of the IRC and condensed it down into basically 1 page of bullet points. Pretty handy for code officials if you just need to, as a handout for your mechanical contractors that can't quite figure it out residentially. And then I've also have a 2-page handout that's just some myths about duct design residentially. So you'll get a copy of Corey's PDF of the presentation and those 2 handouts. And like I said, feel free to reach out to me for any field training or classroom presentations that I could do for you. And I guess with that, we are going to let y'all out about 15 minutes early today, unless Corey had anything else.
Yeah, nothing else. Really appreciate everybody's time and appreciate the questions. And feel free to reach out if you have additional questions. Glad to help anytime.
Sounds good. Thanks for joining us, everyone, this morning. Really appreciate it. Y'all have a great day, and we'll be back hopefully in about 3 weeks. I don't have the next webinar scheduled yet, but we'll get it scheduled soon, and we'll send out email invitations as soon as we do. Thanks, everybody. Have a great day.